Welcome to the Extinct Empire cast. Get ready to embark on an incredible journey through our planet's history, stretching back billions of years.
Billions, yeah. It's hard to even wrap your head around.
Totally. Today, we're plunging into the geologic time scale and the amazing story of life on Earth.
And we're using some great materials from the South Carolina Department of Natural Resources, kind of framed around their educational standards.
Right, so our mission, really, is to understand how Earth's history is divided up, how scientists figured all this out, and, the major events and life forms that mark different times.
Exactly. It's about getting a clear picture of this huge, complex topic. Hopefully you'll get a new perspective on just how old our planet is and the incredible history of life here.
Yeah, think of it as your fast track to understanding Earth's biography. We'll hit the highlights, uncover some maybe surprising facts.
Sound good.
Okay, let's dive in. So fundamentally, what is the geologic time scale?
Well, at its core, it's a system, a way to organize Earth's history into these distinct chunks of time.
Chunks of time, okay.
And the really key thing is these divisions aren't just random. They actually reflect the dominant life forms that were around during those specific periods. We call them geochronologic units.
Geochronologic units, so like a calendar, but marked by life.
Pretty much, yeah. Instead of months or years, you've got these huge spans defined by the biology.
And how do we know what life was like? What's the evidence?
Fossils. Absolutely crucial. The SCDNR materials really stress this fossils, those preserved remains, or even just traces of ancient life. They're our main window.
Right. Without them, it'd be almost impossible to know anything about life millions or billions of years ago.
Exactly. They're the tangible proof of deep time.
The silent storytellers. Okay, so this time scale, it's got layers, right? Eons, eras, periods, epochs. How do they fit together?
Yeah, think of it like those Russian nesting dolls. Eons are the biggest, longest stretches. They're defined really broadly by the general abundance of certain fossils.
Okay, biggest dolls.
Then inside those, you have eras, still massive spans of time, but they're marked by really big worldwide changes in the fossil record. Thanks major evolutionary jumps or, mass extinctions.
Ah, okay. So eons are broad strokes, eras are major chapters.
Right. Then periods are subdivisions of eras. They often focus more on the specific kinds of life that were thriving.
Getting more specific?
Yep. And finally, epochs are the shortest of these main divisions. They show even finer details in life form differences. And sometimes how an epoch is defined can even vary a bit geographically.
So eons, eras, periods, epochs. Each level zooms in a bit more on what life was doing. The source even mentions a specific South Carolina standard, 8.2.4, about this hierarchy.
Exactly. Now, how did this whole thing even get built? It wasn't like someone just, published it one day.
No, definitely not. It must have been pieced together over time, right? The source says put together piece by piece as discoveries were made.
Yeah, which makes total sense. As geologists, paleontologists found more rocks, more fossils, the picture got clearer, the timeline started taking shape.
And the names are interesting, too. You mentioned Cambrian.
Yeah, the names often come in places. Cambrian is from Cambria, the old Latin name for Wales, where those rocks were first studied really well.
Yeah.
Devonian from Devonshire in England.
Yeah.
Jurassic, like the park from the Jura Mountains in Europe.
Okay, I knew Jurassic Park, but not the mountains link.
And Cretaceous comes from Creta, Latin for chalk, because of the big chalk deposits from that time. It really ties these abstract time periods to actual places and rocks.
That's really cool. It makes it feel more concrete. Okay, before we get to the dinosaurs and stuff, what about the really, really early Earth? Hadean, Archean, Proterozoic.
Right, those three together make up what we call the Precambrian Eon. It's like the vast majority of Earth's history.
The vast majority.
Yeah, Hadean is the very earliest, super chaotic, not much of a rock record left. The Archean, that's where we find the oldest known rocks. And the Proterozoic is this huge stretch where early, simpler life really started getting going.
And all the rest of history, up to us right now, is in the Phanerozoic Eon.
That's it. Everything from the Cambrian explosion onwards. It's kind of mind-boggling how much happened before the Phanerozoic even started.
Definitely. Now, you mentioned a distinction, geochronologic units versus chronostratigraphic units.
Ah, yes. It's a bit technical, but important. Geochronologic units are the time intervals themselves. Like the Jurassic period, that's a span of time.
Okay. The time slot.
Chronostratigraphic units are the actual rocks that formed during that specific time. So the rock layers that have Jurassic dinosaur fossils in them, those layers are the chronostratigraphic units.
Got it. Time interval versus the rocks from that time. The source has a chart that shows all this, right? with plate tectonics and dominant life.
Yeah, it's a really helpful visual. It maps out the eons, eras, periods, epochs, gives approximate dates, shows major geological events, dominant life.
Yeah.
Even mentions stuff specific to South Carolina, like the sandhills forming in the Miocene.
Okay, that chart sounds essential. So let's get into the basic rules. How did scientists even start figuring out the order of things before they could put numbers on them? It seems like a massive puzzle.
It really was. And we owe a lot to early thinkers like Nicholas Steno, way back in the 1600s. He came up with some really fundamental principles.
Steno, okay. What did he figure out?
His big one is the principle of superposition. Basically, in any stack of undisturbed rock layers, the ones on the bottom are the oldest, and they get progressively younger as you go up.
Makes sense. The stuff on the bottom had to get there first.
Exactly. And he also talked about original horizontality and lateral continuity.
Horizontality and lateral continuity. Explain those.
Horizontality just means that sediments, when they're first laid down, usually by water or wind, form flat, horizontal layers. So if you see layers that are tilted or folded up...
Something must have happened after they were laid down to tilt them.
Right, and lateral continuity means that these layers originally extended out sideways, sometimes for huge distances, until they either thinned out or hit some kind of barrier.
Okay, so superposition, horizontality, lateral continuity, that's like the basic toolkit for reading rock layers, the foundation of stratigraphy.
You got it. Stratigraphy, the study of layered rocks. And back then, there were debates. The source mentions Neptunists versus Plutonists.
Neptunists thought everything came from the ocean, and Plutonists, volcanoes.
Yeah, basically. Neptunists thought all rocks precipitated out of a giant ocean, while Plutonists, or volcanists, argued for the importance of heat and volcanic activity. These arguments, even if one side was more right, helped push the science forward.
Right, debating ideas sharpens them. Then came James Hutton. The present is the key to the past. Uniformitarianism, that sounds important.
Oh, it's huge. Hutton argued that the same slow, gradual geological processes we see happening today, erosion, rivers carrying sediment, volcanoes erupting, have been happening throughout Earth's history, acting in the same way.
So no need for, constant massive catastrophes to explain mountains and canyons.
Well, catastrophes happen, but Hutton emphasized the power of slow, continuous change over immense timescales. If mountains erode grain by grain, you need a lot of time to wear them down. It implied Earth was incredibly old.
Okay, so the Earth must be ancient, and then William Smith, he brought fossils into the correlation game.
Yes. William Strata Smith, they called him. He was a surveyor working on canals in England, and he noticed that different layers of rock always contain the same types of fossils in the same order. This led to his principle of biologic succession. You could identify a specific rock layer or correlate layers across distances based on the unique group of fossils it contained. The source uses shark teeth as an example. Find the same distinctive teeth, you're likely looking at rock from the same time period.
Wow. So even if the rock type is different miles away, if the fossils match, they're the same age. That's powerful.
It's incredibly powerful. It allowed for correlating rocks globally.
Mm-hmm.
And then Charles Lyell, in the early 1800s, he really synthesized and expanded on these ideas in his book, Principles of Geology.
Lyell, what did he add?
He really hammered home uniformitarianism and formalized other key principles, like cross-cutting relationships. If a feature, say a vein of magma, cuts across existing rock layers, the magma vein must be younger than the layers it cuts.
Makes sense. You can't cut something that isn't there yet.
Exactly. And the principle of inclusions. If you find fragments, like pebbles, of one type of rock embedded inside another layer, the fragments must be older than the layer that contains them.
Right, the pebbles had to exist first to get included. These are like geological logic puzzles.
They really are. And then, of course, Charles Darwin. His theory of natural selection wasn't strictly geology, but it connected deeply.
How so? How did evolution fit in?
Well, the geologists were revealing this incredibly long timeline with layers showing different life forms appearing and disappearing. Darwin's On the Origin of Species provided the mechanism for why life changed over time.
Ah, so the rocks showed that life changed? Darwin explained how it changed through natural selection.
Precisely. Organisms with traits better suited to their environment survive and reproduce, passing those traits on. Over vast geological time, this leads to evolution, explaining the patterns Smith and others saw in the fossil record. The geology provided the stage, the time scale. Darwin provided the plot for the actors, the life forms.
Okay, that makes perfect sense how they connect.
Yeah.
So all this gives us the order of events. Layer A is older than layer B. These fossils came before those fossils. But how do we get actual ages? Like millions or billions of years.
Right. That's the shift from relative age dating to absolute age dating, or geochronometric dating. And this is where radioactivity comes in. It was a game changer.
Radioactivity, how does that work for dating rocks?
It relies on isotopes. Remember isotopes? Atoms of the same element, but with different numbers of neutrons.
Yes, some are stable, some aren't.
Exactly. Some isotopes are unstable or radioactive. They spontaneously break down or decay, transforming into different, more stable isotopes. We call the original the parent isotope, the result the daughter isotope.
Okay.
And the crucial thing is, this decay happens at a very predictable, constant rate. It's not affected by temperature, pressure, or chemical reactions.
Constant rate, like a clock.
Precisely. We measure this rate using the concept of the half-life. That's the time it takes for half of the parent atoms in a sample to decay into daughter atoms.
Half-life. The source had an example. Like, if it takes 4,000 years for half to decay, then after another 4,000 years, half of the remaining half decays, leaving a quarter, right?
Yeah, you got it. It keeps halving. Half, quarter, eighth, 16th, and so on. So if we know the half-life of a specific parent-daughter pair, and we can measure the ratio of parent-to-daughter isotopes in a mineral crystal within a rock,
you can calculate how many half-lives have passed since that crystal formed, and therefore how old the rock is.
That's the core idea of radiometric dating. It's like these tiny atomic clocks locked inside the minerals.
That's amazing. So these decaying atoms tell us the age in actual years.
Yes, numerical ages, billions of years in some cases.
Wow. Okay, the source mentions carbon-14 dating too. Is that the same thing?
It's a type of radiometric dating, yes, but it works differently and for much shorter timescales. Carbon-14 is a radioactive isotope of carbon. Living things constantly take in carbon, including a tiny bit of C14 from the atmosphere or their food.
Okay, while they're alive.
Right. But when an organism dies, it stops taking in new carbon. The C14 it already contains starts to decay into nitrogen-14, and it has a relatively short half-life, about 5,730 years.
So by measuring how much C14 is left in, say, wood or bone or charcoal,
you can figure out how long ago that organism died. It's incredibly useful for archaeology and dating relatively recent geological events, but only back to maybe 50,000, or the source says up to 70,000 years.
why only that far back?
Because the half-life is so short. After 70,000 years, there's just too little C14 left to measure accurately. You need isotopes with much, much longer half-lives to date really old rocks.
Like what?
Like uranium-238 decaying to lead-206. Its half-life is about 4.5 billion years. That's the kind of clock you need for dating ancient rocks.
Okay, so C14 for relatively young, formerly living things, and things like uranium-lead for really old rocks, especially igneous rocks.
Exactly. The source notes that uranium-lead dating is great for igneous rocks because the mineral zircon, which often forms in magma, incorporates uranium but rejects lead when it crystallizes.
Ah. So any lead found in the zircon later must have come from the uranium decaying after the rock formed. Clever.
Very clever. It gives a clean starting point for the clock. And dating an igneous intrusion, like magma that pushed through older sedimentary rocks, can give you a minimum age for those sedimentary layers it cuts through.
Right. The intrusion has to be younger. Are there limitations, though?
Sure. As we said, C14 is limited in time range. Isotopes with super long half-lives aren't great for dating very young rocks. Not enough decay has happened. And there are always possibilities for experimental error or contamination. But overall, it's an incredibly powerful tool.
It really is. It took us from just knowing the order to knowing the actual ages, which leads to the big question, just how old is Earth? The source mentions scientists struggling against, biblical timescale.
Yeah, that was a huge hurdle early on. People like Lyell tried estimating based on how fast things seem to change, mollusk evolution, sediment buildup. Halley tried estimating based on ocean saltiness. Even Lord Kelvin calculated Earth's age based on how long it should take to cool down.
And he got, 24 to 40 million years? Still way off, but much older than thousands.
Right, but his calculation was missing a key piece: radioactivity. He didn't know the Earth had its own internal heat source from radioactive decay.
Ah. So Becquerel discovering radioactivity and the Curies isolating radium, that wasn't just physics, it fundamentally changed geology too.
Completely. It explained Kelvin's error and, more importantly, provided the very mechanism for accurate dating.
So what did that dating reveal? How old is old?
The oldest actual Earth rocks we've found, tiny zircon crystals from Australia, date back to about 4.1, maybe 4.2 billion years.
Billion with a B. Wow.
And meteorites, which are like leftover building materials from the solar system's formation, consistently date to around 4.6 billion years. That's our best estimate for the age of the Earth itself.
4.6 billion years. That's almost impossible to comprehend. And life, when did that show up?
The oldest convincing fossils are stromatolites, structures built by ancient bacteria, cyanobacteria, and they date back to around 3.5 billion years. So life got started relatively early in Earth's history, geologically speaking.
Amazing. The source has that summary chart again, right? Showing the big eras.
Yep. Precambrian, covering that vast early stretch. Then the Paleozoic era, the age of invertebrates, though fish and early land plants, animals came along too. Then the Mesozoic era, the age of reptiles, dinosaurs. And finally, the Cenozoic era, our current era, the age of mammals.
And we're currently in the Phanerozoic Eon, Cenozoic era, Quaternary period, Holocene Epoch. Got it.
But that brings up a really interesting modern question the source raises. Are we actually in a new epoch now? The Anthropocene.
The age of humans, right. Paul Crutzen suggested this around 2000. The idea that human impact since the Industrial Revolution is significant enough to mark a new geological time unit.
Exactly. The argument is that our activities burning fossil fuels, deforestation, agriculture, nuclear tests, plastic pollution are leaving a distinct, measurable, global signature in the rock record, or what will become the rock record.
What's the evidence for that?
Well, the source mentions ice cores from glaciers. They clearly show a big spike in greenhouse gases like CO2 and methane starting right around the 1800s, matching industrialization. That's a major human-driven change to the atmosphere recorded geologically.
So there's definitely a measurable human signal. But is it enough to declare a whole new epoch? That seems like a big call.
It is, and the scientific community is still debating the formal definition and starting point.
Yeah.
Is it the Industrial Revolution? The Atomic Age? The Great Acceleration after World War II? It's complex.
So it's not officially adopted everywhere yet?
Not formally ratified by the international geological bodies as of my last check, but it's a very active area of discussion. But regardless of the formal name, the source makes a key point. It shows geologic time isn't just history, it's ongoing, and we are undeniably a major geological force right now.
That really puts our present moment in perspective. Okay, let's zoom back out and walk through the highlights of life's history, kind of period by period. The source connects this to illustrating the diversity of life over time. Precambrian first.
Right. Early Precambrian, probably no life, very hostile. Then around 3.8 billion years ago, simple single cells, prokaryotes, the later eukaryotes, big moment. Cyanobacteria start pumping out oxygen via photosynthesis, changing the whole atmosphere over hundreds of millions of years. Land masses eventually clumped into a supercontinent called Rodinia near the end.
Okay, then the Paleozoic era kicks off with the Cambrian period, the explosion of life.
Yeah, it's amazing. Suddenly, geologically speaking, almost all major animal body plans we see today appear in the fossil record. Warm seas, lots of oxygen. Trilobites and brachiopods were everywhere. Gondwana, a big southern continent, was forming.
What about the Ordovician after Cambrian?
First animals with actual bones show up. Still lots of trilobites, brachiopods, corals, bits of what would become South Carolina were forming. But it ended with a big chill and ice age centered over Africa, which was near the South Pole then, causing a major extinction. 4 main continents at that time.
Life faces its first big challenges. Silurian next.
Silurian is when life really starts moving onto land. First simple land plants, then the first land animals, probably arthropods. Continents colliding. Laurentia, ancient North America, hit Baltica. Ancient Europe closing an ocean called the Iapetus Sea. Coral reefs thrived, and you get cool creatures like giant sea scorpions.
Sea scorpions. Okay, Devonian age of fish. Sounds like things got serious in the water.
Totally. Fish diversified like crazy sharks, bony fish, lobe-finned fish that were precursors to amphibians. North America was taking shape. Coal swamps formed near the equator. First forests with actual trees like evergreens and ferns appeared. Amphibians made the jump to land. There's also mountain building, the Acadian orogeny, affecting the SC region.
Busy time. Then the Carboniferous, which the source splits into Mississippian and Pennsylvanian.
Right. Mississippian. Lots of shallow seas covering North America, teeming with life like bryozoans and blastoids. First seed plants evolved. Pennsylvanian. That's when you get the vast coal swamps that form today's coal beds. Reptiles evolved from amphibians, crucially, developing the amniotic egg that freed them from water for reproduction. And flying insects appeared.
Flying insects, wow. Okay, end of the Paleozoic, the Permian.
Yeah.
Pangea forms, but something bad happens.
Yeah, Pangea, the giant supercontinent, assembled. Reptiles spread everywhere. The Appalachians rose up, but it ended with the biggest mass extinction ever recorded, the Great Dying. maybe 90% of all species wiped out.
90%? What caused it?
The leading theory points to massive, prolonged volcanic eruptions in Siberia. Huge amounts of lava, greenhouse gases, maybe acid rain. It fundamentally changed the climate and ocean chemistry. Trilobites vanished, along with tons of other marine life and many land species. A truly devastating end to the era.
Unbelievable. But life bounced back, leading into the Mesozoic era, the age of reptiles, starting with the Triassic.
Yep, life slowly recovered and rediversified. The very first dinosaurs appeared, alongside the first small, shrew-like mammals. First turtles, too. And Pangea started to break apart.
And then the Jurassic. This is the one everyone knows.
The golden age of dinosaurs. Pangea's breakup continued, opening up the Atlantic Ocean. Giant sauropods, predatory theropods like Allosaurus, they ruled the land. And importantly, the first birds evolved from feathered dinosaurs.
Right, birds are dinosaurs. Okay, Cretaceous closes out the Mesozoic. T-Rex time.
T-Rex, yes. Also, Triceratops hadrosaurs. First snakes, first primates appeared. Big change in plants. Flowering plants, angiosperms evolved and spread rapidly, becoming dominant. Deciduous trees, grasses became common. But
yeah.
Another mass extinction?
The dinosaur killer. The KPG extinction.
Exactly. Wiped out the non-avian dinosaurs, pterosaurs, large marine reptiles, ammonites. About 75% of species. Strong evidence points to a massive asteroid or comet impact in the Yucatan Peninsula, Mexico. Dust cloud, global cooling, ecosystem collapse.
Another dramatic turning point. And that ushers in our era, the Cenozoic age of mammals. Tertiary period first.
Yeah, tertiary is broken into epochs. Paleocene, mammals started diversifying to fill the empty niches. First horses, tropical plants were widespread. Eocene, grasses spread. Bigger mammals evolved. Early whales, rhinos, elephants. Land bridges connected continents. Oligocene saw the ancestors of dogs, cats, and apes.
Getting more familiar, Miocene.
Miocene, more modern-looking mammal. Horses, mastodons, camels, saber-toothed cats, fossils found right here in South Carolina. The Sandhills region formed. Pliocene, hominins, our early ancestors, appeared in Africa. The Grand Canyon started forming.
And finally, the Quaternary period. Pleistocene and Holocene.
Pleistocene is the Ice Age epoch. Repeated glaciations covered large parts of the northern continents. Modern humans, Homo sapiens, evolved and spread globally. Woolly mammoths, saber-toothed cats were around. Then, about 11,700 years ago, the climate warmed, the glaciers retreated, and we entered the Holocene.
Our current epoch. The age of human civilization flourishing. What an incredible journey through time.
It really is. And all these changes are driven by evolution, by adaptation.
Right. The idea of survival of the fittest. Populations better adapted to their environment survive and pass on their traits. Natural selection.
Exactly. The source used that frog example. Maybe on one part of an island, green frogs blend in better, while on another rocky part, brown frogs do. Over time, the better camouflaged frogs in each area thrive.
It's not necessarily about being strongest, but best suited to your specific conditions. Darwin saw this with the Galapagos finches and tortoises, right? Variations matter.
Absolutely. And the environment itself is always changing, sometimes gradually, sometimes dramatically. The source calls these punctuated events.
Like the big asteroid impact we talked about, that definitely punctuated things for the dinosaurs.
Big time. Block sunlight caused massive climate shifts. It favored organisms that could cope, maybe smaller animals, maybe birds who were descendants of dinosaurs.
Climate change itself has been a constant theme, hasn't it?
Constantly. From the early oxygen-poor atmosphere to ice ages to warm periods, Paleozoic warm seas favored certain life. Those that couldn't adapt when things cooled disappeared. Mesozoic continental drift caused climate extremes. Cenozoic has seen cooling trends, the ice ages, and now rapid warming. Potential drivers include plate tectonics, changing ocean currents, variations in Earth's orbit, those Milankovitch cycles, maybe even magnetic pole reversals.
And volcanic activity. You mentioned the Permian extinction.
Yeah, volcanoes have always been part of the picture, especially in the early. Later associated with plate collision. Massive eruptions like the Siberian traps in the Permian or the Deccan traps in India around the time of the dinosaur extinction can pump out enough ash and gas to drastically alter global climate, block sunlight, cause acid rain, leading to extinction or forcing adaptation.
So these big events, impacts, climate shifts, volcanism, they really drive the major changes we see in the fossil record, leading often to extinction.
Extinction is a huge part of the story. The source notes something like 90% of all species that have ever lived are now extinct. It's the norm, not the exception, over geologic time.
Why do species go extinct?
Usually it's because they can't adapt quickly enough when their environment changes significantly. Natural causes, we've discussed climate, volcanoes, impacts. But the source also stresses human causes now.
Like habitat destruction, cutting down rainforests.
Exactly. Habitat loss is huge. Pollution is another major factor. Air, water, and greenhouse gases driving rapid climate change. This puts immense pressure on species, especially those that aren't very adaptable. It threatens biodiversity, which ultimately threatens resources humans rely on too.
Even though we're adaptable, we still depend on the environment.
Fundamentally. And our main way of understanding all this past life, all these changes, is through fossils.
Study of fossils, paleontology, those preserved remains or traces.
Right. They tell us about the organisms themselves, what they look like, how they lived, but also about the environments they lived in, the past climate.
And there are different kinds, right? Molds, casts.
Yep. A mold is the hollow impression left in the rock. If that hollow gets filled in with minerals or sediment that hardens, that's a cast.
Okay. What about petrified wood?
That's petrified or permineralized. Minerals dissolved in groundwater seep into the organism's tissues and replace the original organic material, turning it to stone.
Cool. And carbonized.
That's when the organism gets squeezed flat, and most of it decays away except for a thin film of carbon, like a silhouette. Think fossil ferns.
And trace fossils, not the organism itself.
Right. Trace fossils are signs of activity. Footprints, trackways, burrows, even fossilized dung called coprolites. They tell us about behavior.
So all these different fossil types piece together the story of life's history, its extinctions, its new beginnings.
It's an incredible puzzle, assembled over centuries of discovery.
Absolutely. So wrapping up, we've journeyed across, billions of years. We've seen how the geologic time scale gives us a framework, how scientists use rocks and fossils and atomic clocks to read Earth's history, and how dynamic life and the planet itself truly are.
It's a story of immense time, constant change, incredible resilience, and profound connections between the Earth and the life it supports.
And maybe a final thought for you, the listener, thinking about the Anthropocene, about our current impact. Where do we fit in this vast timescale? What kind of fossil record is our civilization creating right now?
Yeah, what traces will we leave behind in the layers of rock millions of years from now? Plastics, concrete, altered chemistry, and perhaps even more profoundly, what new forms of life might eventually adapt to or arise from the changes we're making to the planet today?
It's a sobering but also crucial question to think about as we continue to write the next chapter in Earth's very, very long story. Thanks for stepping back in time with us here at Extinct Empire Cast. If you love ancient mysteries, roaring dinosaurs, and forgotten worlds, don't let history stay buried. Hit that follow button. Stay connected with us on YouTube for epic videos, on Instagram for daily fossil finds and prehistoric fun, and right here for more wild journeys through time. Subscribe, follow, and keep digging deep with Extinct Empire, because the past is never truly extinct. And most of all, thanks for your company. It's always more fun exploring the ancient world with you.